leak. For P ReLU, replace leaky ReLU, okay, with P ReLU, and that's it, okay. But for R ReLU, okay, the randomized leaky ReLU, the current Keras doesn't have an official implementation, okay, but you can implement it, I mean, by yourself fairly easily, okay. There's like an exercise at the end of chapter 12 that teach you how to do that. Actually, the textbook, okay, provides a solution for all the exercises in the the notebook, in the notebook, okay. If I remember, but I forgot like where to download it, okay. I mean, there, if you check out the textbook, okay, at the preface, okay, somewhere, okay, tell you like where you can download the Jupyter notebook for all the exercise, for the solution for all the exercises. So you can follow that to see how you can write the code implementation for the randomized leaky ReLU, okay. So for CRU activation, okay, there's like a CRU activation that's already provided by the Keras, okay. So just kernel initial, I mean, just set activation to be CRU and the kernel initializer to be the Tron normal. That's it, okay. So it's something like this, okay. Activation CRU, kernel initializer, the Tron normal. That's it. Okay, so now, okay, we finish the initialization strategy and the activation, different type of activation functions, okay, and we are moving on to the next topic, which is batch normalization, okay. So we know, like using He initialization along with EOU or any variant of ReLU, okay, can significantly reduce the vanishing exploding gradient problems at the beginning of the training. So it doesn't guarantee that they won't come back during training, okay. So this only, you know, sort of like reduce the vanishing and exploding gradient problem from happening, okay. The only one that is more safe from these problems is CRU, okay, but CRU is restricted by the network architecture, okay. If your network architecture doesn't allow you to use CRU for self-normalization, then, well, I mean, there's currently no better way, okay, I mean, to prevent this problem from happening completely, okay, to completely prevent the problem from happening, okay. It's just like it reduces the chance that this problem happens, but it may still come back. So in a 2015 paper, this is a very important one, okay. Sergey Lov and Christian Zgati, okay, these two researchers, they propose a technique called batch normalization, BN, okay, to address the vanishing exploding gradient problems. And more generally, the problem that the distribution of each layer's input changes during training, okay. So, for example, in the Xavier Gorod and Yoshio Benjo's paper, they say it's they didn't give a particular name for this problem, but you know, in this paper, in their Sergio Lofi and Christian Zgati, okay, paper, they gave this name, okay, called internal covariate shift problem. But basically, it's exactly the same problem as what like you know, Xavier paper pointed out, okay, exactly the same. So, but of course, the important thing is not about the name of the problem. The important thing is about what the solution these two researchers propose, this batch normalization. Okay. So the idea, okay, is like this. Okay. They add operation in the model just before the activation function of each layer. Okay. So what operation to add? Okay. They just zero centering and normalizing the input. Okay. So yeah, I mean, because for each layer the variance become bigger and bigger, right? So well, we want to fight with this issue. So very simple. We just in each layer we just try to zero centering and normalize the input. Okay. Then we introduce two additional parameter called scaling the shifting. Okay, we're just scaling the shifting the result using two new parameters per layer. Okay, one for scaling, one for shifting. Okay, so in other words, this operation lets the model learn the optimal scale and the mean of the input for each layer. Okay, so it doesn't, it first like a pull back. It first pull back to make sure like the model, for each batch, okay, the computation, okay, doesn't, the variance doesn't grow, okay, bigger and bigger, okay, but but they also introduced like this scaling and the shifting parameter to make sure like each layer has the proper scale and average. Okay, so in many cases, if you add BN layer as the very first layer of your normal neural network, you do not need to standardize your training set because this BN basically do the normalization for you. Okay, already, and the BN layer will do it for you. Okay, so and also okay. So how does it work? Okay, let's look at this. Okay, so it's like this. Okay, this basically runs for like all the instances in a batch. Okay, most likely it's a mini batch. Okay, so for one mini batch, okay, this X stands for like a particular particular feature. So we just like add up all this feature, for this batch, and then do the average. So we get the average of this feature in this batch, and we compute the variance, the standard deviation, okay, for this batch. Okay, for this feature in this batch, okay, and then okay, you can see we try to for each input we try to minus the mu b. Okay, so we just try to zero centering. Okay, make sure the average becomes 0, and also we divide this by the standard deviation, square root of, square root of sigma stars, sigma square, so it's a standard deviation. So make sure like, the standard deviation becomes like 1. Okay, of course we add a sigma here, okay, a little bit sigma here just to make sure, okay, the denominator can never be 0. Okay, denominator can never be 0 because this square already guarantees greater or equal to 0. Greater or equal to 0. So we add something, a little bit small number, just to make sure this is never 0. And then okay, we introduce a gamma and the beta. So this beta becomes the new average. Gamma is a scaling parameter. Okay. that scale your input. Okay? So this gamma and the beta are additional parameters introduced per layer. Okay? But you can see we first normalize, the features. Okay? And then we introduce gamma and beta. Okay? And this gamma and beta are learnable. Okay? In the sense that we want the neural network, the backpropagation, to learn the optimal gamma and the beta value for each layer, okay, for us, okay? So during training, BN standardized its input, then scales and offsets them. So what about at test time? Okay, this is interesting, okay, at test time. Because, okay, during training, okay, in the training we have a concept of a batch, right? Okay, and you compute the average and standard deviation from that batch. But at the test time or during inference, okay, we don't have a batch. Okay, in a test during inference, we may only use this model to inference 1 or 2 instances, right? So how do you have like the average or like a standard deviation for only a few instances? Okay, there's no way to compute like each input mean and standard deviation. Okay, moreover, even if we do have a batch of instances, it may be too small. All the instances may not be independent and identically distributed. It's not IID, so the computing statistics over the batch instances would be unreliable. Okay, so what do we do? Okay, one solution is like after we finish the training, we run the network through the whole training set. Okay, to compute the mean and the standard deviation for the whole data set. Okay, then we use this final average and the standard deviation for the future inference, okay, for the predictions. This is one way. But, this is not used like in most of the situation. In most of the situation, okay, we use moving average to compute, to estimate like the final statistics during training. Okay, what is moving average? You guys understand the mini batch, right? Okay, the mini batch is like, say we have like we have a class like this, right? So each time I take like 10 students to do training, randomly take 10 students to do training. Okay, so this is like the 10 student is the mini batch that I'm talking about. Okay, so now let's say, okay, I want to compute the average. Say we take an exam, final exam. Okay, and everybody knows your final exam score. And I want to get the average for this whole class. But I do not want to, just collect like the score from everyone and do the average. I just want to, what I want to do is like, during the mini batch process, I would like to, collect some information and use that to estimate the average for the whole class. Can I do that? Each time, randomly take 10 students. Okay, say, each time, okay, this time I took like 10 students. I got the average of these 10 students, say it's 70. And in the next mini batch, I will take another 10 students, right? And then, okay, say the second batch, second mini batch, the 10 students average say 65. So what I'm going to do is like I'm going to, do some average, okay, and use that to represent the average of the whole class I have so far. So normally it's like maybe like it's going to be 65, 0. No, if it's average, just 0.5 times 65 plus 0.5 times 70, right? That's the average. But in fact, what we normally do is like something like this: 0.1 times 65 plus 0.9 times 70. This 70 is the current average that I have for the estimation of the whole class. So this is the current estimation. This is like what I got, like a new input, and I can do this mini batch many times, and eventually, okay, this is going to stabilize, okay, and it's going to stabilize into the average of the whole class. Okay, if you don't believe me, you can write a program to test it. This concept is called moving average. Okay, it's called moving average. Okay, so basically, like you have an estimate for the whole class, and in the next, you get some samples from this population, and you have a new estimation. Okay, so and then you do like a certain combination, okay, linear combination of these two values. Normally, because your estimation normally comes from a larger sample, so you are going to put more weight for this current estimation, okay, and then each time you just keep doing this, iteratively, repeatedly, for many iterations, and eventually this is going to stabilize. This is going to converge into the average of the whole class. Okay, same thing can be done to compute the standard deviation. Okay, can be done for the standard deviation. So we could use like this moving average, okay, to compute to estimate the average and the standard deviation of the whole population. Okay, it may not look obvious to you, but we can hide this computation during the mini batch process, and to get like this job done. Okay, so without the need of like running the whole data set through the network again. Okay, at the end of the training. Okay, so this is like what we can do. Okay. So this Lofi and Sgeti, they demonstrated that batch normalization considerably improved all the deep neural networks they experiment with. Okay, to a certain point. Okay. So leading to a huge improvement in the ImageNet classification task. At the time of when they wrote the paper, the ImageNet classification is the most challenging image classification task. Okay, but of course now, it is no longer that difficult. Okay, ImageNet is a large database of image classified into many classes. If I remember, it's like 1,000 classes, 1,000 classes, and they had this image database is huge. Okay, so commonly used to evaluate computer vision systems. Okay, so this is like a problem, famous problem, like in the old day. We are going to talk about this again when we talk about CNN. Okay, so the vanishing gradient problem was strongly reduced to a point that they could even use saturating activation functions, such as hypertension and the logistic activation function. So if they use batch normalization, okay, they can use even hypertension, logistic, or sigmoid without worrying about the vanishing gradient problem. So this is a very, very strong, very, very powerful technique. Okay, so the network were also much less sensitive to the weight initialization. So even if you don't use a particular weight initialization, it's still fine. It's still fine. So the authors were able to use much larger learning rates, significantly speeding up the learning process. Okay, so specifically, okay, they have this. Okay, applied to a state-of-the-art image classification model, batch normalization achieves the same accuracy with 14 times fewer training steps. 14 times, not 14 steps fewer. 14 times fewer training steps. Okay, so if the original need like 140 times, 140 epochs, now we only need 10 epochs to get the job done. Okay, and beats the original model by a significant margin. So using an ensemble of batch normalized networks, we improve upon the best published result on ImageNet classification, reaching 4.9% top 5 validation error. Okay, I mean, you may not understand what is top 5 validation error. That's fine. Just understand this 4.9%, okay, top 5 validation error and the 4.8 test error exceeding the accuracy of a human rater. Okay, even if you let a human to do the image classification, the top 5 error will be higher than their model. Okay. Of course, this may not be a news nowadays. We all know like in a lot of tasks, like a deep learning model is able to outperform human, right? I mean, nowadays everybody thinks it's nature, but this paper was published in 2015, seven years ago. Okay, so at that time, okay, I mean, they still think like a lot of tasks, okay, human are better, okay, than the deep learning model, okay. So, okay, in addition to these benefits, okay, batch normalization also acts like a regularizer, okay, reducing the need for other regularization techniques. For example, dropout. Okay, dropout, we are going to talk about that later in this chapter. Okay, we're going to talk about dropout. Okay, so batch normalization, however, adds some complexity to the model. Okay, because we need to do some additional computation, even though those computations are not that many. Okay, but still, like it adds a little bit more complexity to the model. Okay, so you know, there's a runtime penalty. The neural network makes slower predictions due to extra computations required at each layer, because at each layer we need to do this, you know, the shift and division, additional division, the shift, and this additional operation take a little bit additional time. Okay, so fortunately, it's often possible to fuse the BN layer with the previous layer after training. Okay, thereby avoiding the runtime penalty. What does that mean? Okay, say like okay, if you want to do like the zero center and divide like this layer by like a certain number, okay, to make like the standard deviation to be 1, okay. You can actually, you know, combine this into the previous layer, okay, because this operation after all are linear, right? And your activation function and everything, the weighted sum, all these are linear as well. So basically, you can combine this, computation in the previous layers. Okay, just change the weight. For example, okay, if you need to divide this by 10, okay, say like you need to scale it, okay, divide by 10. Then in the weight, you just reduce the weight by 10, maybe by 10 times. Then you can achieve the same result without the need of the extra computation. Okay, so here we talk about that detail, but I think like this is relatively easy to understand. Okay, and there's a TF Lite optimizer will do this automatically for you. Okay, but we don't have time to talk about this TF Lite. I mean, which is specifically used for like embedded system. Okay, but yeah, I mean, if you are interested, you can check it out. Chapter 19. Okay, for this type of stuff. Okay, so and also, if you incorporate BN, you will find like the training is slow because each epoch take much more time, okay, when you use batch normalization, because the additional operations that will cost like more time, okay, to process. But okay, this is usually counterbalanced by the fact that convergence is much faster with BN. Remember, like the number of iterations is reduced by more than 10 times, right? Okay. So eventually, okay, it will take fewer epochs to reach the same performance. So all in all, wall time will usually be shorter. Wall time for the training, okay, will be shorter. Okay, this is time measured by the clock on your wall. Okay, so for example, say like if each epoch take more time. Each epoch take twice as much time as previous, but you only need like 1/10 of the epochs. So you are still faster than 5 times faster, right? Okay, so it's going to be something like that. Okay, so it's still worth a lot to use like batch normalization. Okay, so. As with most things with Keras, implementing batch normalization is very simple and intuitive. Okay. Just add batch normalization layer before or after each hidden layer's activation function. So something like this. Okay, let's just look at the code. Okay, so we use like the fashion MNIST again as an example. So input shape is 2828, right? So then, okay, we add Keras layers batch normalization. And we have this dense layer, okay? And then here we use EOU, and we use her normal, okay, initializer. And we have like batch normalization again, and another dense layer, and another batch normalization, and then output layer. So something like this. So easy, right? Adding batch normalization is so easy in Keras. Okay, if you use PyTorch, it's going to be something similar. Okay, very easy. Okay. Of course, like the papers say, like you should apply batch normalization just before activation function. If that's if you want to do that, let me. Here, okay, then it's going to be, first you get a 2828, and then you apply batch normalization, and then, okay, you introduce this dense layer, but here, be very careful. You don't use activation function. Okay, you don't use activation function because you want to apply batch normalization before you apply the activation function. So this is like if you want to implement exactly just like what the paper suggests, okay, the paper in 2015, okay, the Zagatti paper suggests, then it's going to be something like that, okay. You apply batch normalization and then activation, batch normalization and then activation. But here, okay, you need to use bias equal to false, okay, if you want to do it this way. But you will find that, okay, in most of the case, you can apply batch normalization either like this or like this. It doesn't affect the performance of the model a lot anyway, okay? So either way, it should be fine, okay? So this one is like you apply the EOU first and then batch normalization. Okay, so which one to use? I mean, it's really up to you. Okay, you can try either one to see which one performs better. Okay, and here we just want to show you. Okay, number of parameters. Okay, and you can see in the batch normalization, we have this 3,000 parameters, and this batch normalization will have 1,200 parameter, and we have third batch normalization with like 400 parameters, and basically I think that's probably easier. I mean, you can see for each neuron, okay, we have 4 additional parameters in the batch normalization because the previous layer neuron has 300, right? So 300 times 4, we have like 1,200, okay. So same thing, okay. This one is difficult to see, but because the previous layer we have like the input layer is this 28 by 28, 700 something, right? 700 something multiply 4, that's this 3,136. Okay, because remember for each neuron, okay, we have 4 parameters. What 4 parameters? Here, we have this mu b sigma b square, and we have this gamma and the beta. We have these 4 parameters. Okay, but these 4 parameters are not all learnable. Okay, because the mu and the sigma are computed from the batch instances, right? So they are not learnable. Of course, gamma and the beta are learnable. But the mu and the sigma are not learnable. So that's why, okay? So for example, okay, you can see, okay, half of these are learnable, half of these are non-learnable. And same thing, half of these are learnable, half of these are non-learnable, half of these are learnable, half of these are non-learnable. So the total you can see, trainable, okay, learnable, trainable, same thing, okay. So trainable parameter is this many, but we have non-trainable parameter, which is 2,368. This 2,368 comes from half of this plus half of this plus half of this. You can do the math yourself, okay? Because those are mu and the sigma. Those parameters are computed by the batch, okay? So they are not trainable. Okay, and you can see each BN layer adds 4 parameters. So I just already explained this. Okay, so we can look at the parameters of the first BN layer. 2 are trainable, okay, and the 2 are not trainable. Okay, the trainable ones can be adjusted by backpropagation, and non-trainable are not affected by backpropagation. So you can see here, okay, the gamma, beta are trainable. So we have true. I mean, they are said to be true. So the other, like moving mean to be false, and moving variance to be false. These two are the mu and the sigma, and these two are the gamma and the beta. I mean, that's presented in the equation. Okay, and also, okay, we have like additional operations. Okay, for each mini batch, because remember we need to estimate the average and the standard deviation for the whole data set. Remember, I just mentioned like those moving average concept, right? So for each batch, we need to do additional computation, which is like presented here. Okay. So I already finished this part. So so the batch normalization class has quite a few hyperparameters you can tweak. Okay. So default normally will be fine. Okay. You normally don't need to tweak them. Okay. But you may occasionally need to tweak such as momentum. Okay. This hyperparameter is used by batch normalization layer when it updates the exponential moving average given a new value v. This is like to compute the average and the standard deviation for the whole data set. Remember, something like this. So this one is the v that I'm talking about here. Okay, this is called exponential moving average. Okay, so so it's a v times momentum plus v times v hat times momentum plus v times 1 minus momentum. Okay, so this momentum, okay, this v hat is like the current estimation for the whole population. This v is the whatever like I mean you get from this batch of sample. Okay, and this momentum, as I said, like normally it's like a big number, a number close to 1, a good value, a number close to 1, such as 0.9, 0.99, something like that. Okay, basically you want more nines for larger data sets and the smaller mini batches. Okay, because smaller mini batch just means they are the new set of instances value are not that trustworthy, so you will get like you will try to get put like a lower weight to it, because say if it's like a 0.999, then you put this one for here for the current estimate for the current estimate. So the one that you get for the new sample, because it's compared to like the whole population, this one is relatively small, right? So this is a little bit more, what should I say, not that stable. So 1 minus, for example, 0.99, this weight is much lower, right? Something like that. Okay. There's another hyperparameter called axis. Well, let's take 10 minutes break. When we come back, we will continue the discussion of this. Okay, we're almost done with the batch normalization anyway.